Well, here we are. Let's take a look at actually chapter 7. Point 2, and it is working still with integration by parts, and I'm going to show you a little bit of a shortcut today. It's called the tabular method, and tabular method can be used on just a specific type of integration problem. And for these problems, we're looking for a problem where if I took the derivative of a function, it would eventually go to 0. So if that's the case, and the other portion can be easily integrated, then tabular method makes sense for this problem. And why don't you go ahead and write down the 3 columns unless they're already on your note sheet. But we're going to say, what do we select as U? What should we select as dV? And then the sign business, that'll make sense in just a minute. All right. So when I think about lyate, it tells me to look for logs. I don't see any logs. I look for inverse trig. I don't see any inverse trig functions. And then my third kind of priority is, are there any algebraic expressions present? And yes, I see one algebraic expression, the 4x squared. So that is what I'm going to set up to be my u. So I would let u equal 4x squared. And then that's going to, of course, force e to the x dx to be my dv. So go over here to the right and let's set up 4x squared under the u column. And let's take e to the x in the dv column. In the u column, this is where I kind of think we're going down. We're taking derivatives. Okay, this is the derivative column. And go ahead and proceed through taking your derivatives. That'll give me 8x, 8, and 0. Eventually, I ended up going to 0. That's the type of problem I can use tabular on. In the dv column, this is the column where I'm going to integrate, just as we would with normal integration by parts. And the integral of e to the x, you know what, let's make this just a little bit more interesting. Let's call it e to the 3x, okay? Just to make it a little bit more difficult when we're integrating, because I'm sure you'll hit those type of problems in homework. So let's call this e to the 3x. When I integrate e to the 3x, I get itself as well as a correction factor of 1/3. If you did use substitution, you'd find that 1/3. Think about, now just check back. If I took the derivative of 1/3 e to the 3x, it would definitely swing me back to there. So I know I have the correct integral. And I integrate again, e to the 3x, well, it's e to the 3x. And then I'd have it times 1/3 times the previous 1/3 gives me 1/9. And this will give me e to the 3x times 1/3. So bump that up one more and I'm at 1/27 e to the 3x. Perfect. The next step is to draw in the diagonal line. You're going to connect your very first derivative with the integral. So that's like taking u times v, isn't it? And do that again and again and again until you get to the bottom column. Oh, I'm not sure I mentioned, I integrated all the way until I reached the 0 from the derivative. So I knew I had 4 steps over on the u side, so I needed 4 steps over on the dv column. Now we've got our diagonals drawn, and you start with a plus sign, and the next one's a minus sign, and then it's plus. They just alternate as many as you need. And now the answer, yes, we come to the answer this quickly. The answer becomes the product of this diagonal, and the sign is going to lead it off. So I have a positive 4/3 x squared e to the 3x. Now I'm down to the next one. 8x times 1/9 e to the 3x, and it will have a negative with it. So negative 8/9 x e to the 3x. The next one now, I'm taking 8 times 1/27 e to the 3x, and its sign is positive, so I have a plus 8/27 e to the 3x. And our final part is the plus c. That is the answer. It's that easy. Tabular is very sweet. It makes very quick work of integration by parts. Had we done this the traditional method, we would have had a couple integration by parts within that one to continue to do because of the algebraic expression going on and e to the 3x continuing forever. So how do you analyze it and decide if you can use tabular? Well, once again, I'm looking to see, do I have a function that will eventually zero out if I take its derivative? Yes, I have such a function, that algebraic function. Cosine is a function that's easily integrated. So that's going to be my dv. This will be my u, and we can set up tabular. Maybe even pause this video and see if you can set it up on your own. So make your u column, your dv column. My u column starts with x cubed. I know to take the derivatives until I get to 0. So one extra line on this one. And next, the dv was cosine of x. If I integrate cosine, I get sine x. If I integrate sine, I get negative cosine x. If I integrate negative cosine, I get negative sine x. Remember, we talked about the pattern work when you're integrating a trig function like that. And if I integrate negative sine, I am going to get negative cosine. I got to check my work here. Something seems off a bit. Derivative of sine gives me cosine. Derivative of negative cosine gives me positive sine. Derivative of negative sine gives me negative cosine. Here's where I'm off. Just need that. And then the integral of negative sine will give me positive cosine. And I just check back and make sure my derivatives work, right? Take the derivative on each of these steps and work your way through. Got it laid out. I knew I had to take 5 of them to match up with how many derivatives I needed. And now we're going to draw in the diagonals. So get a diagonal, 4 diagonals. Add your signs, it's going to be plus, minus, plus, minus. And now it's just writing out the product of them. So I've got a positive x cubed times sine x. Minus minus becomes plus. See where I picked up minus minus? So a negative times a negative gives me positive 3x squared cosine x. The next diagonal has a positive with a negative, so this will be minus 6x sine x. And another minus 6 cosine x. Finally, plus c. And see if I can identify my solution here. There is the integral for problem number 2. Sweet. I don't think you need more problems on that, but the type that can be done are those that end up being easily integrated and the derivative goes to 0. So then I come to problem 3 here, and I look at it, and both of these items are very easily integrated. But if I chose one of them to be my u, I noticed that it would not zero out. Matter of fact, it would just continue on and on and on. That type of scenario where the derivative will just keep cycling and the integral is easily done is what I think of kind of as a circular type integration by parts. And you'll see what I mean with the idea of circular here in a minute as we proceed through the problem. Now, what should I choose as my u and my dv? Honestly, it probably wouldn't matter too much in this case, but I'll follow the pattern work. No logs, no inverse trig, no algebraic. Hit the trig function. Okay, I'll make cosine my u, and I'll make ex, e to the x, my dv. So, just standard integration by parts. My u will be cosine x. My dv is going to be e to the x. And e to the x dx, I guess. If I take the derivative, that'll give me du equals negative sine x dx. And if I take the derivative, or the integral of dv, I get v, and e to the x is simple, it's e to the x. All right, so let's draw out our integration by parts solution here. So put down your left side where we're starting the problem. The integral of e to the x cosine x dx is equal to u times v. So e to the x cosine x minus the product coming across the diagonal v du. And I see I have another negative, so that'll force that to a positive, e to the x sine x dx. Well, I don't know the integral of e to the x sine x. Matter of fact, I should use another integration by parts. So here we're seeing those multiple uses of integration by parts within an integration by parts. If I originally set up my u to be the trig function, then I want to stay with that. So I'm going to set up u to be sine x, and dv will be e to the x once again. The derivative of u is cosine x, and the integral of e to the x would be e to the x. So now I'm going to expand and solve that particular problem using integration by parts. Let's go ahead and rewrite the entire problem as we get ready to do that next line or that integration by parts work. All right, so I hit integration by parts. When I hit that integral, it's u times v, so plus e to the x sine x minus the integral of v du, so that would be an e to the x cosine x dx. And you're like, holy cow, this is just never going to end. And you're right, it would continue on and on because of the kind of circular nature of these two functions. They continue on and on. So what do you notice though? Here's what I hope you're kind of seeing. I have this integral, which is a complete match to that integral. Since I have like terms in a sense, I can add them together. So now we're kind of going to go into a algebraic step here. We're going to add the entire integral to the left side. So I'm going to move it from the right side, swing it over to the left side, and ask you, how many integrals of e to the x cosine x do I have? And the answer would be, you have 2 of those integrals. So I put a 2 out front. And I have e to the x cosine x plus e to the x sine x. And now what I'm going to do is multiply both sides by 1/2 to get rid of the 2. And we will end up with an integral of e to the x cosine x dx equal to 1/2 e to the x cosine x plus 1/2 e to the x sine x. And let's not forget our c plus c. There's the solution. We found the answer to the integral of e to the x cosine x. I think it's very circular in nature because this does wrap back over to the left side and kind of completes the process for us. So that's all the notes for today. And the homework is 8 problems. It hopefully there'll be some standard integration by parts. There should be some tabular. And I even told you to use tabular on that very first one. And think about liate when you're selecting them. And there you go. Good luck.